Hello, everyone. Dan here speaking from Cornell University. Today, I'd like to talk about some of the work that we're doing right now and some of the ideas and thoughts that we've been discussing, not just with the people listed here, but with a lot more people throughout the last year. And so, my talk will be about the role of different temperature targets when determining the outcomes of climate engineering and when trying to determine trade-offs. And the main question is, how do we choose a scenario for SAI simulation and what is a scenario? So SAI simulations of stratospheric aerosol injection and of climate engineering in general do not exist in a vacuum. And the impacts of SAI don't exist in a vacuum either. It's very hard to say SAI would do X without explaining exactly what scenario we're talking about. And what is a scenario? So multiple ways to define them. And unlike the scenarios in the IPCC report, for instance, that just have different storylines for emissions, when it comes to SAI, that gets even more complicated. So here's some examples of previous scenarios that were used when determining the effects and impacts of SAI. We have G4, one of the first geomip experiments with injections of SO2, where we have a baseline emission scenario of RCP 4.5, and then we have a net forcing that is constant because it's produced by a constant injection of SO2. And the injection goes from 2020 to 2070, and then it's just stopped all at once. Then we have glance here, where we have an RCP 8.5 scenario when it comes to emissions, and then SAI is used to keep temperatures at 2020 levels. And then finally, we have G6, part of GeoMIP, but more recent, where we have a underlying scenario that is at tier one, so a high forcing scenario, SSP 585, very similar to RCP 8.5. And we use SAI here to bring temperatures down to a medium scenario, so SSP 245. These are just three examples. There are many more, but this has been widely used for impact analysis. And so it's interesting to see how they all do different things. The aim of SAI is very different between these three scenarios. So there are various things to consider when we talk about what's our scenario, what our scenario for SAI simulation should be. What questions are we trying to answer? Are we trying to just answer some physical question? Do we need a very high signal to noise ratio? And then how do our choices fit into the larger discussion on climate change scenario? That everybody will know by now that there's a huge discussion on whether some very high forcing scenarios like RCP 8.5 make sense, considering that that's not what we are on track for. So do we when we choose our scenarios, we should consider that too. And finally, but probably more important, what were our goal with SAIB? What are we thinking that SAI should be doing? And that's strongly what I'm going to try to show you is that how that's strongly going to affect what then we can say SAI would do. Another way to look at this is from this figure, at least from this paper that Phoebe and a lot more people, me included, published at the beginning of 2021 when discussing the potential ecosystem impacts of SAI. So on the left, we see something that looks a lot like Glenn's. So no climate change mitigation, very high emissions. And then someone says, okay, let's simulate SAI on top of that. Can we use SAI to bring that down to a temperature target? Probably yes, at least we can simulate that. But there are various problems with that. There's a higher risk of potential ecosystem impacts. There is a risk for a sudden termination risk. And mainly, the fact is that what we keep saying all the time is that we do not want to imagine SAI as um, something that can replace cutting emission. So then we see a scenario like the one on the right. We have from high emission, we assume that we're cutting emissions a lot. We actually also assume that we do CO2 removal to try to reach some temperature targets somewhere in the future. And then we ask, can we use SAI to bring back temperatures down to the temperature target even before CO2 removal and emission cuts have managed to work? So can we avoid any kind of overshoot? And that probably is the way in which you want to think SAI more. And in general, it's probably a way that also has the risk for less ecosystem impacts. So this is kind of our summary idea of the amount of things that one needs to consider when developing a scenario for SAI. So, and this was the only way in which I could summarize the incredible amount of dimensions that get into deciding a scenario. Where do we decide to go? How much would we want to cool with SAI? It's important. Do we want to stay at 1.5 degrees above for industrial? Do we want to go further down than that? Because 1.5 was something that was decided because it was in reach in a way. But if SAI could cool more, should we at least try to understand what impacts that would have? That's one example. The other one, of course, like is where will we be? So what underlying emission scenario there is. But then even if we make just these two choices, then there are many more choices to make. Like when do we start? Of course, we cannot start last year because that's gone, and probably we cannot start in 5 years because there's no technological capabilities. But will it change anything if we start our simulations in 2035 or in 2045? Can we kick the can down the road, or should we start as early as possible to minimize some impacts? And when we decide what kind of SAI we're going to do, there are various strategies. We've shown that plenty of times now. There isn't just one way to do SAI. We could be injecting at different locations, at different altitude, to manage different goals that are not just global mean temperature. And then when we do even just these four choices, then there are more. What about what if other things happen? So what if for some reason SAI gets interrupted? What effect did that have? What if we want to stop it at one point? What's the best way to stop it? So there are plenty of things to consider here. So now we go to our particular choice of scenario for the future simulations that we're running. That most of them have been run already, but there are more to come. So first of all, for instance, I took this figure from the UNFCCC report, and this shows that the national determined contribution as of the end of 2021 kind of track in terms of global greenhouse gases emissions, they kind of track SSP 245. They do not track any of the more optimistic scenarios, definitely. We would need to do a lot more to keep temperatures below 2 or 1.5. But that's where we are right now. This is probably definitely better than being on track for one of the higher emission scenario, but it still means there's probably going to be looking at the multi-mean model from IPC from KIMIP 6, probably we would be looking at still 3 degrees of warming, and we know how dangerous it's going to be. So being there means that we can both have our scenario tied in reality. This is probably for now where we're going, hoping that nations respect actually their NDCs. But we're not anywhere higher, and we're also not trying to imagine a scenario like a 1.5 that is probably very hard to see happen in the foreseeable future. So here there's the temperature in the model that we're using right now, which is CSM2, the community or system model. And here I showed the temperature from 1990 all the way to 2070, and for just one ensemble member. But this is just to give you an idea of when temperatures above 0.5 above pre-industrial were reached, when temperatures above 1.1 Celsius were reached, and when the model projects that 1.5 would be reached. That here is around 2030. And then where it's going. So clearly a continued warming under SSP 245. And this is the kind of framework we've decided to do our new SAI simulations. And this is an idea of all the simulations that we like to run, that we've run in place. And you see, there are very many questions that we can answer here. So, can we use SAI to stay at a temperature threshold that is the one from the Paris Agreement? But why stop there? Why stop there? Not because we want to do more, but we should explore more. So, can we actually use SAI and bring back temperatures at 2020 levels? Can we actually use SAI? This is all starting in 2035 and go back even closer to pre-industrial. So we have different thresholds, different temperature targets. What happens if we start not in 2035 but in 2045? And then what happens if we terminate? What happens if we try to gently phase out SAI? And we've only decided to simulate all the way to 2070 for computational constraint, but also because we think that this is a better way to just focus on the medium term and for now not concern too much ourselves with what will happen in the long term, where we might have new informations to inform our decisions. Some preliminary results, of course, because we've already seen it before, injecting SO2 here at 4 locations, the same as Glen, so 30 north, 15 north, 15 south, and 30 south, we can reach different temperature targets. They require, of course, different amount of SO2. Staying at 1.5 requires 10 teragrams by 2070. Going to 0.5 above industrial requires almost 30 teragrams of SO2 by the end of the century. And what's interesting is that these different simulations do different, as we expect, they do different things to different metrics. These are just some examples that were easy to analyze and just a place to start. This does not include any impact, every impact, but things that people usually look at. P minus E, so precipitation minus evapotranspiration, the amount of available water changes in the different simulation. The extent of September sea ice in the Arctic changes depending on them. So we might want more or less, but if we want more sea ice, we might have less water availability. And there are also some interesting things here. So the model simulated NPP kind of doesn't change in the 3 scenarios. Same for stratospheric ozone in the southern hemisphere in October. Is not very sensitive to the amount of SO2. AMOC changes in different ways. So does the ocean heat content. So these are all things to consider. Um, this is just another example of, for instance, the optical depth increase, what the sulfate in the stratosphere would look like, and what we would see from the surface. There are clearly some differences here. And other differences, like changes in stratospheric temperatures. Of course, the more we inject, the more we warm the stratosphere. That changes the dynamics of the stratosphere. That changes ozone in many ways, and changes, for instance, water vapor in the stratosphere. Again, these are just some examples of all the things that we have the potential to look at here. So having different temperature targets allows us to understand how linear some of these responses are, for instance. Finally, as I said, we also simulated some events that could happen. So you see here, what would happen to global mean temperature if we delay the start by 10 years, 2045? What happens if we suddenly stop SAI, and what happens if we phase it out? And this is very interesting because in this case, at least, it shows us that due to the fact that the optical depth and the sulfate in the stratosphere doesn't disappear immediately the moment you stop, there isn't actually that much difference whether you immediately stop or phase out in 10 years. And we want to explore that more. Also, what happens if we stop SAI for 1 or 2 years? Here it looks like there is some form of detectable response, but in the global mean temperature, but it's kind of tiny. So, but there could be various impacts that we can see in those simulations that are not represented in the global mean temperature. So to conclude, choices for SCI deployment span multiple dimensions. It's very hard to catch them all, but in our modeling, we should try to consider a variety of scenarios to reflect that, so that we can say, oh, we should stop saying SAI would do this and that's all. We should, in context, say SAI might do different things depending on what we do. And of course, not just global mean temperature will be important in this case. Thank you.